and endomorphism C going from E squared to E squared, which is a crossing. And this is kind of extra structure that doesn't have any obvious relation to SL2. There's nothing about SL2 that tells you this is the right thing to choose. So why is this here? I mean, hopefully that'll be a little clearer once we do some examples. The important thing is these guys give us extra structure and they appear in all the interesting cases we want to do. Okay? So somehow the justification for this definition is you can prove lots of things based on proving that something is a categorical SL2 action, and there are lots of interesting categories that carry SL2 actions. So those two things together are exactly what you look for in a good definition. That there actually are examples, and that you actually learn something by seeing something as an example. All right, and these guys satisfy these slightly mysterious relations, which are some nil version of the symmetric group relations. So the big difference is in Alistair's talk, if he had a bicon like this, that would be the identity. In my talk, that's 0. And you know, Alistair never brought in dots, but you might expect there to be a naive commutation of dots past crossings, you know, like the sort of naturality property in Alistair's talk, and that's not quite right. It's close to right. It's true that there's a relationship between dot here and dot here, but the difference is the identity. All right. And then I had this slightly funny, and we talked a lot about kind of, well, this is really the right definition, but this is a little easier to check. Something which definitely does directly come from the SL2 relations. This is kind of a direct categorification of the SL2 relation that the commute E and F is equal to H. That's what these equations represent. All right. And then finally, I had this funny little technical condition of Y is nilpotent, and if I apply E enough times, it gets 0. All right. Well, I probably shouldn't call this a generalization. The idea was this was a generalization of the example that I asked you to do as an exercise. All right. So the kind of first kind of really interesting example, actually all the examples I showed you before were essentially special cases of this, is I look at partially symmetric polynomials. So I have some list of indices, and I look at polynomials in variables z, and I partially symmetrize them. So I break my variables up into blocks, and I assume that my polynomial is symmetric under permutations inside those blocks. And then I mod out. So that's the elementary symmetric functions of the full alphabet. I could just say I mod out by positive degree symmetric functions. So like, I think in Peng's notation, you would write this as, you know, I have my CZs. I look at invariance under SL plus. So that generates the same ideal as just all the elementary symmetric functions for I positive. All right, and this is a very natural ring to consider. For example, if all of these K's are 1, it's the covariant algebra. And it actually has a geometric incarnation. It's the cohomology of a partial flag variety, where what the KI's are telling you is what's the gap between the dimensions of successive flags in the flag variety. So what's happening here is on this partial flag variety, I have a tautological vector bundle, vi mod vi minus 1, and the elementary symmetric polynomials in one of these smaller alphabets are the Chern classes of vector And this relation is sort of saying that if I take the whole vector space, that's a trivial vector bundle. These are its Chern classes, so those are 0. So if you like geometry, that's the way to think about it. But this is also sort of a purely algebraic thing, and everything you're going to say, you can do purely algebraic. All right. So what I want to consider is the modules over this cohomology ring for the Grassmannian. So this AKLK, I'll just emphasize, this is the cohomology of the Grassmannian of K planes in N space. All right. And what my E and F are is, well, if I take one of my buckets and I break it up further, then the thing with bigger buckets is a subring inside the thing where the buckets are more broken up, right? So if I have K, L minus K, that means the first K things are symmetric, the last L minus K things are symmetric. And I can look at these polynomials, K minus 1, 1. So now I only require the first K minus 1 things to be symmetric. Well, that includes all the things where the first K are symmetric or some. It includes, for example, the one variable that corresponds to my 1. I'm still symmetric over these last guys. So probably should have, right. And geometrically, what this corresponds to is if I take this partial flag variety, where now I'm going to have 3 steps. So this is, I have 2 subspaces. I have 2 different maps to Grassmannians, where I remember one of the subspaces, and I remember the other subspace. And this inclusion is the pullback map in full range. But it's also just the obvious map of I require less symmetry, so I have an inclusion of rings. And my functors E and F are, I just take this bigger ring, I think about it as a bimodule in the 2 possible ways, and I tensor with it. Okay, so I just want to kind of draw your attention here. In E, I'm taking K things, L minus K things, and I'm pulling 1 off from the K things. In F, I have K things, L minus K things, and I'm pulling 1 off from the L minus. All right, so this is looking at a smaller subspace inside a K-dimensional one. This is looking at a bigger subspace that contains a K-dimension. And I've written both versions of this map between partial flag varieties here. So this one corresponds to E, this one corresponds to F, starting at K and minus K. Oh, I'm sorry, that N should be an L. All right, so those are my functors E and F. Well, I need to tell you a little bit more. I also need to tell you what these endomorphisms Y and Psi. All right, so the endomorphism Y, I just want to emphasize this because it's maybe a little unclear, right? What's happening here is I have my first K variables. I have my last L minus K variables, right? And when I'm doing E, I'm pulling off this variable and saying it doesn't have to act symmetrically with all the ones from Z1 up to ZK minus 1. So in this algebra is essentially I take these things, the things that are symmetric in K, and L minus K, and then I say, oh, wait, actually, ZK is allowed to just be there on its own. It doesn't have to get symmetrized with everything else. So multiplication by Z minus K is an endomorphism of this bimodule. It commutes with the action. I mean, this is a commutative ring. So multiplication by any element of this big ring commutes with multiplication on the left or the right by the smaller rings. So I'm thinking of this ZK as an element of this bigger ring. All right. If I do E squared, so there's a little bit of commutative algebra behind why this is so, but believe me, it's true. That's the same as taking K minus 2 things and symmetrizing them, and then having 2 variables that sit on their own. Right? So when I do E squared, I would draw this as 2 guys. So multiplication by this guy corresponds to ZK. Multiplication by this guy corresponds to ZK minus 1. And now there's a thing I can do that commutes with the action of K, L minus K, commutes with the action of A, K minus 2, LK minus 2, right? So the two things that are acting here, I just give myself a little more space. Thinking of this guy on one side as a module of K, L minus K, and on the other side as K minus 2, L minus K plus 2. So I'm looking at this guy as a bimodule over these guys. So I could do something that commutes with the action of these guys, commutes with the action of these guys, but is not a ring homomorphism. And it's this divided difference operator. So I can anti-symmetrize for these 2 variables in the middle. And after I do that, I have to get something that's divisible by ZK minus 1 minus ZK. And so this operation sends this ring to itself, but sort of like these kind of trace homomorphism, trace maps that Penn was talking about, it's not a ring homomorphism. But it will commute with things that are symmetric in ZK minus 1 and ZK. Right? If I multiply F by something that's symmetric in these 2 variables, it stays the same here. And so the whole thing gets multiplied by that. So since things here are symmetric under switching K minus 1 and K, and things here are symmetric under switching K minus 1 and K, that's a bimodule homomorphism, even though it's not an algebra homomorphism. It's bigger algebra. And this is kind of a general rule about C. It's always something about this kind of divided difference operator. So one way to think about where these relations come from is they're how polynomials commute past divided difference operators. All right, are there any questions?
There's a geometric motivation for C as well.
For C?
Yeah.
I mean, yes. In these terms, yeah, I didn't leave myself enough space on the page. So where C comes from is I'm looking at the partial flag variety, right, where I have a K minus 2-dimensional space, a 1-dimensional space, a K minus 2-dimensional space, a K minus 1-dimensional space, a K-dimensional space, and then the whole thing, right? And so what C is there's a map down to forget that middle space and only choose a K minus 2-dimensional space and a K-dimensional space. And C is push forward by this map and then pull back by a control. So the reason that's a divided difference operator is the Atiyah-Bott formula for integrating over the P1 corresponding to that map. Right? This is a map whose fibers are P1s. So integrating over it decreases the degree of your cohomology class by 2. That's where the C comes from. All right. Any other questions? Okay, so I have a bunch of things I'm supposed to check. I have a bunch of categories that correspond to the integers. Yes, I've successfully defined a category. I told you a ring, you can look at modules over that way. I need these functors to be adjoint. That's actually not totally obvious because they're both written as tensor products. And if I want a tensor, if I want the right adjoint of a tensor product, that's actually going to be a hum. So I need to use the fact that these are what are called Frobenius extensions. So you should think of this as sort of, I have these maps, which are about as nice as maps between manifolds get. They aren't just product maps, but the fibers are always complex projective spaces. And on the level of cohomology, things kind of behave like it's a product. So I'm basically using Chuang-Rouquier duality for the projective spaces, which are the fibers of this map. That's why I'm calling it relative Chuang-Rouquier duality. But the kind of technical term to look for is Frobenius extension. You might have heard Chuang-Rouquier duality tells you that the cohomology of a compact manifold is a Frobenius algebra with a good trace. Such that you could always multiply any element of the ring by something and get non-zero trace. This was also getting used at the end of Bond's talk. All right. So I'm just asking you to believe me that you actually have this isomorphism of functors. And once you know this, then it's obvious that they're adjoint. This hum is the right adjoint tensor. Okay. I also have some relations I need to check. So I'm not going to go through all of these, but the key thing is, why does this relation hold? And as I say, that's the relation for how polynomials commute past divided difference operators. So I've just written down the proof for you here. And I write this as, that looks like a C, but it's actually supposed to be a C. When I multiply by y and then act by c, what does that actually mean as an endomorphism of bimodules? It means that I take f, I multiply it by zk minus 1, because it's y tensor 1. And then when I act with this k minus 1k, that flips to a zk. So, well, I would like to divide out by zk minus 1 minus zk, but that doesn't exactly work out here. So I rewrite this quotient where I pull out a zk, but I had to add and subtract a copy of f times zk. I end up with this extra term here, and I exactly get f plus 1 tensor y cf. And that fact that here I get a zk instead of a zk minus 1, that's what accounts for the fact that I need this term. All right, and then finally, I need to check that I actually get the sl2 relations. And it's enough to check this acting on a free module, because then I can just tensor my whole calculation with any other module. So when I do this on a free module, I basically just use these facts multiple times. If I look at a k1 L minus k minus 1 as a k L minus 1 module, it's a free module of rank L minus k. If I look at k minus 1 1 L minus k as a free module, it's rank k. And again, both of these are coming from the fact that I have complex projective spaces as fibers, and this L minus k and this k are the rank of the cohomology, the sum of the Betty numbers of symmetric functions. It's also not hard, but I always think about it geometrically. So now when I compare EF and FE on KL minus K, well, I apply these twice, and I see that I get a bunch of copies of KL minus K. And I just have to check that the numbers are different by the right amount. So I get k minus lk plus 1 for EF, and L minus k plus 1 times k for FE, and the difference indeed is L minus 2k, which is what I wanted. This is in the L minus 2k weight space. All right, and there's this E property that's obvious, right? This is a finite dimensional graded algebra, so any positive degree element of it is nilpotent. And if I apply E a bunch of times, well, every time I do E, I decrease K, and so eventually K becomes negative. And by definition, those weight spaces are all zero. All right, cool. So there actually is a kind of big class of interesting examples of modules sl2 categorifications. And one thing I kind of skipped over because I was going a little fast. This is actually really a special thing. It's essentially the unique way of categorifying simple representation of sl2. Slight exaggeration there, that's not quite right, but it's close to being true. So I denote this script L.
The precise statement is it's the unique one where the highest weight category hyperspaces.
Yes, right. Where there's simple highest weight object with no self-extensions. All right, cool. So I fear this is going to set me back a lot on time, but I think it is worth mentioning. There's another way to think about this categorification, which is instead of looking at these polynomials, I look at the nil-Hecke algebra of a rank K. So I had defined this last time, but let me just say it again. And of course, I screwed up my indices. I take K strands, and I look at the K ways of putting dots on them, the K minus 1 ways of crossing adjacent strands, and I look at the algebra those generate with the familiar relations. That's the nil-Hecke algebra of rank K. And this acts on polynomials in K variables via multiplication for the dots and divided difference operators for the opposite. So this is another way of kind of making precise this thing I said about these are the relations between polynomials and divided difference operators. And inside here, there's a central subalgebra, which is the symmetric polynomials. The symmetric polynomials obviously commute past this time, so they're centric. And I had gotten a question earlier about like, why do we have these dots? Why do we need them? What's the point? Well, the point is they make this theorem work. If I take this nil-Hecke algebra, it's actually a matrix algebra. It's a matrix algebra whose rank is k factorial times k factorial. And it's matrix algebra over this central subalgebra, the symmetric polynomials. And the way I prove this is actually when it acts on A is a free module of rank k factorial over the symmetric polynomials. And the nil-Hecke algebra is the full endomorphism algebra of that free module, which is why it's a matrix algebra. So that gives me a Morita equivalence between NH and the symmetric polynomials. One way I like to think about this, because I like to kind of put everything in geometric terms, this NH, it's the equivariant cohomology of the full flag variety times the full flag variety. And that acts on the equivariant cohomology of one copy of the flag variety by Ginsburg and Chris, using convolution. And that's this action above. And there's one special element taking the half twist of all the strands with no dots. That acts by this operation, which had come up in Pong's talk, of anti-symmetrize and divide by delta. This is the polynomial that she was calling delta. Sorry? Oh, you were calling it lambda? Oh, I'm sorry, it looked like a delta. Okay. Well, many other people call it delta. I guess she was calling it lambda. Okay. No, it's the GLN equivariant cohomology of things, which is the T equivariant cohomology of a point. Talk about this later. We don't have time for it. This guy corresponds to the full, the fundamental class of flags times flags, and it acts on A by integrating over flags, which is what this operation is. It's integrating over the full flag. And so by Poincare duality, A has a dual basis under this pairing, and you can write explicitly down this isomorphism to the matrix algebra by sending Eij to this dual basis multiplied on the two sides of this half twist. So this is really a very explicit thing. I mean, that basis has a nice description in terms of Schubert polynomials. All right. So anything I had said in terms of symmetric polynomials, I can say in terms of this Nilhek algebra. And one really natural thing to consider for this Nilhek algebra is the cyclotomic quotient. So I consider this full Nilhek algebra, and I consider the two-sided ideal generated by the first dot raised to the alpha. Okay, well, I took a quotient of a matrix algebra. Any quotient of a matrix algebra is a matrix algebra over some quotient of the base rank. So this has to be a matrix algebra with the same rank over some B that's a quotient of symmetric polynomials. And it turns out that that quotient is exactly the cohomology of the Grasshopper, which we can write as a quotient of symmetric polynomials by complete symmetric polynomials whose degrees are too large. I think I'm going to skip the details of this because it doesn't really matter that much. I'm pretty low on time. I'm happy to talk about it later. All right, but there's sort of a slightly more natural way of cooking up this action when we think about things in terms of Nilhek algebras. So I have an inclusion map of the Nilhek algebra on k-1 strands into the Nilhek algebra on k strands. And this is literally, I have some picture and I add another strand to its right. And it turns out, if you whack it, so this makes NHKL into a bimodule over k-1 strands, k strands. And when I whack this with the Morita equivalence, I get the bimodule that I had before. Or, you know, the magic of Morita equivalence. So these operations I had written before as tensor products, and these terms I can write as induction and restriction for this inclusion of Nilhek algebras. This whole diagram. Okay, so since we just kind of transferred everything by an equivalence of categories, we find that these induction and restriction functors define an SL2 action, this category where the L minus 2k weight space is NH of L.
Right, you showing an HLK, that's the quotient by the Y1 to the L.
Yeah.
So the deal?
Yeah. And I think I reversed this. I made the upsetting realization last night that because of how I'd written everything, these guys are obviously adjoint in the wrong direction. And it's a theorem that if they're adjoint in one direction and they define an SL2 categorification, they're also adjoint in the other direction. And I was very annoyed and tempted to switch E and F, but that would have made life so much more All right. I realize I should probably mention, right? You should sort of feel like there's a lot of things happening here that sound like things that we're paying for, right? Like it just there must be some connection here, and I want to do my best to describe that connection. So I can look at modules over. Sorry, it should have been. Of course, my indices are wrong. GLL. And I can tensor, oh no, there's so many n's that are wrong here. I can tensor with the natural representation and its dual, which of course also connects to Alistair's talk. So these are translation functors. And I can define a natural transformation from this functor to itself by multiplying by this Casimir. So this is an element of the universal enveloping algebra, tensor the universal enveloping algebra, and it commutes with the image of the co-product. So when it acts on the tensor product, it acts by an endomorphism of that tensor. And so it gives me a natural transformation of this functor tensor with a finite dimensional element. And for any complex number A, I can define, well, look at tensor product with natural representation and look at the generalized eigenspace for A of this omega. And on the other hand, I can tensor with the dual of the natural representation. And for funny numerical reasons, I want to look at the n minus A. Of course, that should be an L eigenspace for this same guy, the Casimir, acting on the tensor product with the dual of the natural representation. And it's a theorem, it's proven in Chuang-Rouquier, that these functors define an sl2 action on category N. Or more generally on any category of modules where the center acts locally finitely. So for example, anything that's finite. There's sort of a nice intrinsic but slightly confusing way to describe the weight spaces, which is I look at these traces. This is trace, and it's a relative trace from Hong's talk. And I look at the powers of the Casimir. I build a power series from that. That turns out to be a rational function. And I look at what order of zero it has at u equals A. And that tells me what weight space is. And the way this connects to this L, scripty L of \ELL is I can look at the anti-dominant projective in this extremely singular block of category N. So I'm writing down a particular weight here. How did I choose this? Lambda plus rho is anti-dominant, and lambda plus rho is stabilized by SK, SL minus K. Or I could say that this guy is stabilized by this guy under the dot. So this is a self-dual projective. Its endomorphism ring is exactly this cohomology of the Grassmannian. It's AK L minus K. And when I act on this guy by E0 and F0, I get other projectives of the same form with some number of copies. And the subcategory of these projectives, this is the projective injectives in these particular blocks of category O, generate a copy of L. And of course, there's a much more general story here, but this is kind of the closest connection I can find between those other talks as well, without getting too deep into this.
Sorry, you're saying that at C then you figure out which EA and you figure out how EA and FA act according to looking at the power series and determining where is the zero order N. And at that point A is which A you pick? Or,
no.
Oh.
For every A, I have functors EA and FA.
Yeah.
Those generate an SL2 action. When I tell you that statement, I have to tell you what weight every object has.
Okay.
On any simple, this power series acts by a rational function, depends on what the symbol is. It's a rational function whose roots, zeros and poles depend on, for example, the highest weight of the symbol in a relatively straightforward way. So I could have told you this in terms of the highest weight, but it's actually a little ugly when you try to do that. It's much nicer to write this. Okay.
So for every A, we get a subtraction?
Yes.
So, but you always get the same copy of L of L, you said? Or,
Well, on these specific.
oh,
So no, I made a very specific choice here. This is for E, F, and F, E0 and F0. What's true in general, right? I have all these different copies of SL2. What I actually get an action of is the Kac-Moody algebra, whose Dinkin diagram is C with the adjacency relation under +1. And on any particular block, only finitely many of those contribute. But
you have a bunch of copies of like A and B.
yes, a bunch of copies of A and B. Yes.
So the action on the entire category of is categorification of modular.
It's a category. So if you look at integral blocks of category O, it's a categorification of the module C infinity to the tensor L over SL infinity. There's actually some beautiful stuff about superalgebras where if it were SL L/N, it would be the natural representation tensor the dual of the natural representation.
SL2 is a root SL2 lattice.
Yes, right. Yeah, exactly what's happening here is I'm telling you the individual root SL2s, and then there's something a bit extra to check that you're getting, that all of those interact in the right way. All right. Are there any more questions? So I actually want to, have other agendas for this this talk. Right? There's a lecture series where I talk about hidden planets. So if you want to hear that stuff, you have to bug me at other times. What I did plan was to talk about modular representation, which of course often has a similar kind of flavor to category O, but it's a little bit different. So, just how the timing ended up, this lecture just ended up being examples. So we just saw some examples. Here are some more examples. We're going to look at representations of Sn, and I won't explicitly discuss them very much, but the same principles apply to lots of generalizations, Schur algebras, Q-Schur algebras, Ricci-Koike algebras, etc. All right, so consider the usual symmetric group with its usual set of generators, Si. Alistair already discussed those, so I don't need to worry about it. And of course, I just decided not to use that notation anyways. There are natural elements in the group algebra of this. So this is in KSN. It's not an element of Sn because I'm taking the sum, called the Eustace-Murphy elements, where I pick an index K and I sum all the transpositions that switch K with something lower. So there are a couple of key properties of these guys. One is there's a nice relation for K plus 1 in terms of XK and SK plus 1. So if I take XK and I conjugate by SK plus 1, what I do is I swap every one of these Ks to K plus 1, but I'm still missing one of the transpositions, the one that swaps K plus 1 and K. I have to add that on to get this relation, right? And the other interesting property this XK has is that it commutes with SK minus 1, which means it commutes with XJ for all J less than K. So it commutes with this group algebra, and inside this group algebra is XJ if J is less than K. So this actually shows you generate a commutative subalgebra of the group algebra. Actually, a fact which isn't that important for us, but which is nice to know, is that actually the center of the group algebra is generated by symmetric polynomials. So these are not central in the group algebra as a whole. If you take symmetric polynomials, they will. All right, so I want to do something very analogous to this Casimir story I just had for GLM. I'm going to look at an Sn module, and I'm going to restrict it to Sn minus 1. And when I do that, because Xn commutes with K of Sn minus 1, Xn acts on this restriction by an endomorphism. It's a natural transformation from the functor restriction to its sum. And there's dual natural transformation of induction, which is slightly more annoying to write down. Now, if you sort of start thinking about this theory of adjunctions, you don't even need to write this down. The induction is adjoint to restriction. So if I have an endomorphism restriction, I automatically get one of induction via this picture. But I can also just write it down explicitly. Induction, right, is tensor product with Ksn over Ksn minus 1. So if I have something that acts on the right on Ksn, muting with Ksn minus 1, that's an endomorphism of this representation. By multiplying the right by the use of Murphy, and that gives me an endomorphism of induction. All right. So when I do this, it gives me a decomposition of both the restriction functor and the induction functor. And maybe I should have, did I say this here? Throughout, let K be a field characteristic P greater than or equal to 0. So I include characteristic 0. So it turns out the eigenvalues are all in the integers. And so I get that the restriction and the induction break up as a sum over the elements of Z mod P. And of course, remember here, if P is 0, that just means over the whole integers of these summings. E sub A, that's I do restriction and I look at generalized eigenvalues of Murphy. Or F of A, that's I do induction. And I look at eigenvalues of these. And I encourage you as an exercise to compute some of these. It's instructive to do some small computations over F2 for small rings. All right, for those of you who like the representation theory of Sn, let's talk about how this connects to polynomials. So if I have a partition, I have a Young diagram. And of course, we'll draw these as boxes. You can think of it as a subset of the set of pairs, positive integers. And I'm going to be very interested in a property that every one of these boxes has. It has a content, which is what column it's in, minus what's right. So at the very bottom of my Young diagram, I have a 0, and as I go out, this statistic increases because I've increased the column. As I go up the column, it decreases. So let's first talk about the characteristic 0 story, which I assume many of you know, but it's worth putting out there. There's a bijection between representations of K of Sn, this is only for characteristic 0, and partitions of N. So lambda gets sent to what I'll call S lambda. This is the Specht module. Noting this version of this module, which is defined over Z, which will be useful later. But it's only simple for all partitions if the field is characteristic 0. So in this characteristic 0 case, what happens? Well, I act with E or F on the Specht module, and I always get another Specht module or 0. The rule is E tries to remove a box of content A. EA tries to remove a box of content A. FA tries to add a box of content A. If you can successfully do that, then EA or FI sends a spec module to the resulting spec module. If you can't do that, you get 0. So for example, here I sort of tried to illustrate this with the partition 4, 3, 1. So hopefully the colors come out okay. For example, here I have an addable box of content -3. So when I do f of -3, it's going to send the spec module for 431 to 4311. And if I do f of -1, there's an addable box of content -1, so it sends 431 to 432. On the other hand, if I did f of 0, I would be trying to add a box of content 0, and I would say, well, shoot, I can't do that. There's no addable box there, so that means that f of 0 acts by 0. And just as I had this power series in terms of the Casimir in the GLN case or GLL case, it's actually very helpful. Ooh, these guys ended up a little cheek by jowl. Sometimes you can move things around a little too much. It's helpful to think about the power series. It's a little strange. I'm taking the usus Murphy's. I'm writing a formal power series whose entries are symmetric polynomials of the usus Murphy's, which, as we now know, are central in the group algebra. So this is in the center of K of Sn. And I write this rational function. I'm doing the expansion at u equals infinity. The wrong series. I know this looks a little strange, but it's worth thinking through what this does. So on the top here, right, I have a difference of squares. So on the top here, I have u minus xi minus 1, u minus xi plus 1. And actually, there's a nice formula for how this acts on any spec module. It acts by the product of u minus the content of the addable boxes in the numerator divided by u minus the content of the removable boxes. Now in characteristic 0, there will only be an addable box or a removable box. So what this will be telling you is zeros of the numerator are the addable boxes, wholes of the whole thing. Yes.
So why does it suffice to look at the eigenvalues of Xn in the sense that for the carton, you can remember the eigenvalues for all the elements?
Why does it suffice?
But you define the sl2 action by just looking at the eigenvalues of Xn, but you don't care about X1 to Xn minus 1.
That is true, I don't.
Yeah, so I'm just making an analogy that.
Well, those are not endomorphisms of the functor, so that doesn't make any sense. So, I mean, if I want to understand that, right? So one way to build the spec module is to start with the unique representation of S0 and then apply FIs to add boxes of the content I want to, right? And in fact, which chains of FIs, starting on that trivial guy, will get me a spec module. They're exactly the chains which are take a standard tableau on your partition and read off the contents of the boxes labeled 1, 2, 3, 4, 5, 6. So that's where the eigenvalues of the smaller xi's come. Right, so the analogous thing to think about for representations of Lie algebras isn't the torus, it's the action of central things. So this is sort of the analogous GLN. Again, I'm looking at endomorphisms of my functor. The torus isn't central, so it doesn't act by endomorphisms of things. All right, so are there any questions about the characteristic 0? Sorry, I mean, I know there's of actual experts on the audience, so it's slightly embarrassing, but somehow you should know this. All right. I want you all to know this, so if any of you don't, I'm glad to explain.
Just a question relating to the other case. So in this case, we're doing all the symmetric groups together at once.
Yes,
And that, whereas in the other one, we're fixing a single yarn, but like you can say this in SL2.
yes. Yeah, well, life is like that sometimes. Yeah, that's a good point that also happens. All right.
Should get away with time.
Oh shoot. Oh. Okay. Well, I mean, I can at least make the statement. Okay, so for k of any characteristic, I still get the symmetric polynomial. So on a simple, it acts by a power series, and the roots and poles of that are going to be in Z mod PC. So I can look at any simple and I can define the order of the root or pole. And in fact, if you think a little harder, this is true for any indecomposable. I have an indecomposable module. I'm going to get the same power series on every simple that appears as a composition. All right. So I can take my representations of Sn. I can look at this order of polar zero for this power series acting on any composition factor, and I can look at the subcategory where I think modules where vectors have a pole or a zero in particular. And then I can sum over all n. So again, I had mentioned this thing about wanting a sum of finite dimensional modules. This is a sum over all n of looking at a particular idempotent times k of Sn times that idempotent. But so each one of these algebras is finite dimensional, but I want to consider them over all n, so taking infinite sum. So theorem, the functors E and F define a categorical sl2 action. I don't know how, I don't know exactly when I started. I usually haven't been starting on that very precisely at 30 class. So I don't know.
Well, I think you've done 50 minutes, 2 minutes, 4 minutes.
All right. Well, yeah, well, let's just stop here and we can talk about this more next time.